Now that we have some understanding and some theorems built up about connectedness and compactness, we can go back to our calculus days and reprove some very important theorems, namely the intermediate value theorem and the extreme value theorem, among some others. But these two have particularly nice proofs using connectedness and compactness ideas. And in fact, I have their simpler like calculus versions here, but in the intermediate value theorem, in the topology setting, you don't actually have to have your codomain be the real numbers. It could be any topological space with an ordering property defined on it. By that, I mean, I want to be able to say certain numbers are less than or equal to other numbers, because the whole point of the intermediate value theorem is to be like, okay, here's f of b, here's f of a. If I were to pick some y value between those, then there would be some corresponding x value producing it. So that's generally our mental picture for intermediate value theorem, but maybe you can see how that would be extended to really any kind of topological space where you're allowed to compare numbers or compare elements in ordering sort of way. Similarly for the extreme value theorem, which again is reproduced here in its calculus-y version, instead of saying, okay, there's some maximum value that gets attained and some minimum value that gets attained. If you start with some closed interval as your domain, you're actually allowed to change this closed interval to any compact set. Of course, in the real numbers, compact is the same as closed and bounded, so it makes sense to just work with this in the calculus case. But in general, you can work with compact spaces. And the proofs for those are not much more complicated than what I'll show here. But yeah, let's prove these simpler calculus theorems using topological ideas. So where do we want to start? Well, we'll start with this picture, right? So I had drawn A mapping to f of A and B mapping to f of B. And we're imagining taking some y value. Maybe I'll draw it in yellow. So there's y. And I want to say that since this function is continuous, it has to correspond to some x value down here. And indeed, that'll be true. The way we can see it uses the idea of connectedness. So we know we're starting with a closed interval in the real line. So I'll say since AB is a closed interval in R, it is connected. And that's something we didn't prove, but hopefully we just trust is true. It's not terribly difficult to prove, it's just kind of tedious. It certainly looks like it should be connected. And what else? Well, since f is continuous, what do we know about continuous functions applied to connected sets? Well, we know they map to other connected sets. Connectedness is preserved by continuous functions. So I'll just say the image, f of AB, is also connected. And it's also a subset of R. So by the Heine-Borel theorem, what do we know? Well, or sorry, not by Heine-Borel, but by just the fact that all connected sets are intervals, we know it's an interval. And indeed, it looks like it's some interval. It's not quite the interval from f of A to f of B, because we actually go above it and below it in certain parts. But it's some interval. It's some connected space in the, on like the y-axis. So we're just calling it f of AB, but it is an interval in its own right. Okay, so we know it's an interval. Furthermore, we could note that f of A and f of B are certainly contained within this interval, right? Elements of this image. We can see that here. The whole interval is like this whole thing projected to the y-axis. F of B and f of A are definitely within that interval. And so what can we say? Well, the fact that y is actually between those two means it's also in the interval. So in fact, y is in the interval as well, right? That's a property of intervals. If you have, if you have two elements of the interval and some value between them, that also has to be in the interval. That's what intervals are. You can write out the definition if you want. Okay, and what does this mean? If y is in the image, that means there exists some corresponding x in that domain, such that f of x maps onto that y value. And that's exactly what we were hunting for. That exactly matches up to this. We started with some y value and correctly found the x value mapping onto it. And we didn't have to do anything with the completeness of the real numbers. We didn't really have to do much analysis at all. We just had to know connected sets in the real line are intervals. And that's basically it, other than what the definition of an interval is. So the topologist proof of the intermediate value theorem is much nicer, in my opinion, than the analyst's version. How about extreme value theorem, right? So this says, again, we're starting with some continuous function on some closed interval. Here I said we could replace this with some compact interval if we wanted to. But it'll suffice to show this. Then we actually get some x values, one of which corresponds to the maximum attained value and one of which corresponds to the minimum attained value. So let's actually put those on this graph just so we have something to look at. So the min would have been x2, I suppose, with the convention I'm using. The max is x1. Okay, so I'll just write max here. Actually, let's give it a name. Let's call that D and we'll call that C. You'll see why in a second. All right, so what do we know? Well, we know we're starting with a closed and bounded interval in the real numbers. So since AB is closed and bounded, this is where I meant to apply the Heine-Borel theorem, my little slip up earlier. That exactly means it's compact. And again, we didn't prove the Heine-Borel theorem, but hopefully it's familiar enough. So a closed and bounded interval in the real line is automatically compact and vice versa. And what do we know about the relationship between continuous functions and compact sets? Well, since f is continuous, and since this interval is compact, continuous image of a compact set is compact. So I'll just say, since f is continuous, this image is also compact. Great. And where can we go from here? Well, it's compact in the real line. Again, so just kind of undo what we just did. It's compact in R, hence It's a closed and bounded. And in fact, for similar reasons outlined in the previous proof, we can call it an interval. And let's just give it a name. Here you should see why I actually picked some things. Okay, so let's go through that really quickly. This is a compact set in the real line. Heine-Borel says that means it's closed and bounded, but it also has to be connected. Since the set we started with was an interval, intervals are connected, continuous images of connected sets are connected, and then that means the image is connected, so it's an interval. So it's a closed and bounded interval. And what does that give us? Oops. Okay, so we have that interval actually laid out here, right? It's this interval. And in fact, we know exactly what we need to here. In particular, since this is a closed interval, I'll just say now, let's focus on the upper end point. So D being in the image here, right? It's closed, so of course it is contained in this set. What does that mean? That means there exists some, I'll call it x1, in that domain, such that f of x1 equals D. And similarly for C, right? C is in, again, it's a closed endpoint, so it has to be in this. This time we'll say, okay, since it's in the image, call it x2 this time, ends up mapping on to C. But that's exactly what we wanted up here. We had some x1 value mapping onto, in this case, D is the maximum value, and some x2 value mapping onto C, which is the minimum value. Why are they the max and min, you might ask? So let's just write this out. D is the maximum. And C is the minimum. I don't know why I wrote 0, 1. It's effectively the same proof, but being more general. So why is that true? Well, CD is the image here. So of course, the largest value in that interval has to be the maximum attained function value. And similarly, C being in this interval means C is in here, but C is smaller than all other images. So it's the minimum function value. And I'll just say this proves the result. So ta-da, we are able to say, yeah, if you start with some closed and bounded interval, that means it's compact, which means it maps to some compact interval on the y-axis. That means that's going to be closed and bounded. And automatically, just from that being closed and bounded, you get that there have to be some points mapping onto those extreme values. And that's how we prove it. So nice and easy. Much cleaner than what you would see in analysis. You know, epsilons or deltas or completeness axioms or anything like that. Just some nice clean theorems we've proven topologically applied to the real analysis context. Thanks for watching.